We're going to move on now to Mike Zemcov. Mike Zemcov is not here at APL, but he has been extremely active with the program from the beginning. We're very pleased to have him today talking about an astrophysics augmentation to the mission. Mike, the floor is yours.
Thanks very much, Michael. So I'd like to thank the APL team for giving me the opportunity to give a kind of report out about what we've been talking about the past few years. Specifically thinking about what astrophysical questions might be interesting and unique to do on a platform like ISP, and then secondly, how we're going to do it and how we might mesh with all the other very interesting stuff that's going on. So next slide. Really briefly, just like to thank it's not really a formal team, it's kind of a loose agglomeration of field experts, ranging from people like Chaz Bikeman, who's been thinking about a thing like this since before I was born, all the way down to, us younger folk. I guess I'd like to highlight Casey Liss, who has been our sort of minder and point of contact back to the ISP team, and Andrew Poppy, whose models you'll see in a second, but has done a lot of work trying to model the dust cloud in the solar system. Next slide, please. Okay, so real quick, let's justify why we would ever consider augmenting the payload in the first place. I think Kirby made a really great case about doing planetary science, and that sort of stands on its own. But whether we're talking about planetary or astro, the fact of the matter is you're adding risk and taking away resources by sharing. So, a few things are evident here when you think about it really quick. One is that the astro case that we think makes sense here is going to be doing high impact science during what is a relatively quiet time for the mission, namely right at the beginning, the first 5 years. And effectively that time is it's not that it's underused or anything by the helioscience, but this is just like added bonus. And just to sort of motivate the high impact, somewhat to my surprise, occasionally, the kind of EBL science, extragalactic background, and other things that I'm about to talk about do get picked up by news outlets. So just from earlier this year, there was a result from New Horizons that Todd Lauer and collaborators measured the optical background using the LORRI camera, and that got picked up by the New York Times. Other things have been picked up by like Forbes and Scientific American and all these outlets. I think there's a lot of interest in the public for this kind of science, and so this is just kind of a way to kind of bolster ISP so that stuff is getting produced from the very beginning. As Pontus mentioned, I think the additional risk and requirements we impose by design are relatively small. That is not zero, but we're really not adding too much in terms of complication. I also think, thinking back to perhaps pioneer days, which was a long time ago, mind you, and perhaps Voyager as well. Back then, I think there was a sense at NASA of let's just go out and do really cool science. So we're not going to silo it into these different divisions. That came later with how funding is done at NASA. And it would be great, and I know this is a big political lift, but it would be great if we could really get back to this idea of, boy, we get to go to the outer solar system so rarely, we should really make the most of it. And if that means we have to sort of, break these silos down and figure out how funding would work and all that, we should do that because it's worthwhile. It really only improves our knowledge of the universe as a whole. Also, I want to make the case real quickly that some of the science questions we're asking actually overlap with the heliophysics science. I think ISP is kind of sitting in a really cool space where there's a lot of crosstalk between these different things. How does the outer solar system work? It's a really good question, and I think it's not broken down according to the traditional, tripartite sort of way that these things get thought about. So anyway, that's kind of why we should talk and why we have continued to talk. What we got charged with, this small group, sort of 3-4 years ago, was basically to sort of think through science cases that we can do from this distant solar system, and then try and come up with an instrument that could be reasonably realized for a 2030 launch, which I recognize has slipped back a little bit, but the baseline still obtains. Okay, so next slide. Okay, so just to run through the possible science cases, I'm not going to have time to talk about all of these. What we kind of came up with as a laundry list are measuring backgrounds, so the light from all the stuff outside of our galaxy, looking at our galaxy itself, looking at ice and dust in the interstellar medium, looking at similar kind of compositional questions and distribution questions in our own solar system, looking at the dust there. We could also imagine doing a very deep exoplanet transit survey. So looking for stars that are getting occulted by exoplanets. We could imagine looking for microlensing of events that are being done by dark planets, things that don't live around stars that we see from time to time in the galaxy. It ends up, if you can see those events from two different baselines, you can break the degeneracy of the distance and mass of the lenser, and uniquely come up with what the lenses, what the properties of the dark lens are, and that's how sort of 10 solar mass planets that are in the intergalactic space get discovered. We could do rapid follow-up of transient events, so things like gravitational radiation events. We could have a platform that would allow us to see that on the other side of the sun when Earth is not at a disadvantaged place to see it. And then finally, people talk a lot about solar gravitational lensing, which is using the sun itself as a gravitational lens to look at distant objects. If you want to see more about this, if you're all interested, there's a paper that's sort of geared towards New Horizons, Zemcov et al. 2018. That gives a pretty long, detailed breakdown of all these different things. Okay, so next slide. We can break these down really quick into things that require basically passive survey, in the sense that we can kind of do them along the way, and we don't really need to have that great pointing control for a very long time. So those are sort of in the top bracket there. We can look at things that require more active pointing control, which would involve like sitting and staring at a spot on the sky for weeks or months at a time. And then the final thing, the solar gravitational lensing is challenging for a variety of reasons, but one of the biggest ones is you have to get rid of the emission from the sun, and that would require something like a coronagraph, which is great, but really getting outside the envelope in terms of complexity for what we think we can do. So based on these kind of considerations, if you go to the next slide, we kind of were immediately able to pick out those sort of bottom items, which are very interesting. I don't want to say they're not, but I do want to say they're kind of hard to do, at least from ISP as currently envisioned. So we're really interested in what amounts to the diffuse sources, things that you don't really need very fine pointing control to look at. And those are the things that are listed at the top there. Okay, if we go to the next slide. So just to give you a sense of how this works, when you observe the sky brightness with a small telescope from the inner solar system, what you're seeing is light from dust in the solar system, sunlight that's getting reflected back. We call that zodiacal light. That's the blue band in that image at the top there. Plus you see the light from the galaxy, which is the sort of yellowy red stuff in the middle. And then behind all that is the light from everything else in the universe that isn't in our galaxy. So that's what you observe. If you're interested in decomposing these things, so you can study, each individually based on its own merits, you have to figure out how you're going to subtract things out or model them out. So the zodiacal light has traditionally been removed by basically making a very good model for it and subtracting it. That doesn't work so well because, in fact, the image up top is kind of cartoonish in the sense that the blue band should be very, very much brighter than the galactic light. It's a very bright signal. So it's difficult to model out at the sort of 1% level so you can get at these other kinds of science. The second thing you can do is get away from the sun, which is the ISP approach. And that's actually better because you don't have to worry about how well your model is doing. Then secondly, you'd be stuck with light from the galaxy, or you would study the light from the galaxy, you'd make a model for that and remove that basically by observing at long wavelengths and then scaling that down using empirically determined scaling relations. And what's left over is basically the light from outside the galaxy. So those are the sort of decompositions that we would be thinking about doing with these data. Next slide. So the first science case is dust in the solar system. These models shown on the left from Andrew Poppy basically can be decomposed into three populations of dust. Stuff coming from the Kuiper belt, which is green, stuff coming from the Oort cloud, which is blue and sort of isotropic and doesn't really end because the Oort cloud extends out so far. And then dust from Jupiter family comets, which is the red stuff, which is actually the dominant source of dust in the inner solar system. Just to sort of give you a sense of what this looks like, the upper right is an image actually from Earth, which I've set sideways to kind of highlight the fact that you know, the sun really is sitting in a disk of dust. And we have to be able to account for that, and we have to be able to study that because it is interesting in itself. So after a lot of head scratching and talking about how this might work, we actually decided that what's happening here is as you go out in the solar system, the insolation is reducing as 1/r². So that means the brightness you observe in scattered light is going down as that factor. And that means that as we get out past 10 AU out to 20 AU, the zodiacal light that we would measure in the sort of optical and near infrared becomes very, very faint. And you can see that in the lower right plot there, which is showing kind of the spectrum as we go out. On the other hand, the thing that isn't changing is actually the thermal emission from the dust. So the way to go after this kind of, if we're interested in, for example, the Kuiper belt dust, which would allow us to compare to similar images of exoplanetary systems and perhaps understand the structure of the Kuiper belt better itself, you really want to do that in the thermal infrared. This dust has a characteristic temperature of tens of Kelvin, and by going out and measuring it, tens or 100 microns, you can really get a handle on what the structure of that emission is as we go out. So that's kind of the philosophy there, is that we would do sort of near infrared measurements in the inner solar system out to perhaps Jupiter or Saturn, and then we would switch over to doing far infrared sort of characterization and try and test these models that Andrew and others build. Okay, next slide. Another thing we can do is look at diffuse galactic light. This is really, tying into interstellar probes, probing of the local interstellar medium. In fact, doing remote sensing of the local interstellar medium is quite difficult, which is a good reason why to go out and sample it directly. But there's this issue of like, how do we tie that back to our understanding of the interstellar medium, the galaxy as a whole? So if we were able to build a near to mid IR spectrometer, we can do the kind of measurements shown in M82, which is a galaxy outside of our own, where what we're really able to do is measure emission from polycyclic aromatic hydrocarbons and other organic molecules, as well as constrain things like the relative contributions of carbon and silicate dust, and really probe organic molecules. This is sort of an understudied region of astrophysics, at least in the sort of high latitude diffuse part of the galaxy away from the galactic plane. So this is a sort of unique opportunity to really get down and study that stuff and understand its relationship to things like star formation and so on. Okay, next slide. Finally, the extragalactic background light is a very interesting science topic, and it's one because this EBL, this light from all the galaxies outside of our own, is 10 or 100 or 1,000 times fainter than the zodiacal light from Earth. It's very difficult to do properly from Earth. We really want to get away from it. So, what is this light? Why is it interesting? Well, basically, what I'm showing here is an image of the history of the universe from the Big Bang at the left up to the present day today. I won't go into the details of that, though I could answer questions if you wanted to. Basically, the EBL, at least in the infrared wavelengths that we're talking about measuring it, is integrating all the emission from everything after the first stars formed. And so as a result, it's really a constraint on the process of stars and star formation in the universe. And it really lets us, it's a tight constraint that models for that have to be able to meet. So as I said, it's been very difficult to do from Earth. So if you do the next slide, This is a compilation of current measurements that's pretty recent. What you can see is a sort of hump on the left, which peaks around 1 or 2 microns. That's due to direct emission from stars. And there's a hump on the right, which is a little bit less well-defined, that peaks around 100 microns. And that's due to thermal emission from dust and galaxies. And together, these two pieces of information let us really understand how do stars form, statistically speaking, and how do they evolve and emit and tie into the overall energy budget of the universe. And so the unfortunate truth is that because this is a very difficult thing to do from Earth, largely because of the zodiacal light, the measurements are all over the place. You can see this as a log plot on the left. In the infrared, we don't really understand this number to better than a factor of 2 or 3. The far infrared and the mid infrared, sort of from 10 to 100 microns, there is even worse. And that's because the zodiacal light just is completely dominant. It completely blows any other signal out of the water. The only way to ever get a measurement at these wavelengths at sort of 20, 30, 40 microns that's going to be any good is really to get out of the dust, is going to require something like ISP. So that's a really strong science driver. So our goal here in terms of sensitivity is really to drive down to the 1 nanowatt level. That's a unit we use on the y-axis there. That would really let us fully constrain what light from galaxies we should be aiming at. Okay, next slide. So in terms of flow down, this is the Pontus's very, very succinct traceability matrix. Of course, we're trying to do basically 3 different types of science, and those each have their own requirements. And I didn't want to bore you for 10 minutes showing you the full flow down, but I guess just to summarize real quick, what all of these things really have in common is you want to be doing low resolution spectroscopy, imaging spectroscopy, with a pretty big field of view, degrees on a side, and then trying to do that over as many wavelengths as you possibly can, hopefully from optical all the way out to the far infrared. That would be ideal. So that's what kind of got captured into this requirement matrix. If you go to the next slide. So what we sort of envisioned might fit the bill here is this concept. I of course, I'm not promising that what eventually gets built would actually look like this, but this is basically extrapolating from known technologies and solutions, and then packaging it into a basically what would fit into a CubeSat based on some work we've done trying to do this kind of thing from CubeSats, which fits the bill because CubeSats are necessarily small and light. The ISP instrument would have to be small and light in order to get accommodated. So basically what it is a 3-optic, 3-mirror off-axis telescope design that you then couple through a beam splitter to a near-infrared focal plane that would cover from 0.5 to maybe 15 microns, and then a far-infrared focal plane that would use a different technology of detector and go out from perhaps 30 out to 100 or so. And then what you do is you just package that in such a way that it was thermally shaded and emitting the heat out to space to cool it down passively, and you could easily get to 20 or 30 Kelvin that way. Okay, next slide. So just to give you a sense briefly of what this kind of thing could do, our sort of baseline design would be from 0.5 to 15 microns, doing imaging spectroscopy with a linear variable filter type solution, and then a multi-band far infrared mapper that would be making sort of maps of the far infrared sky. The primary aperture would be, order 7 centimeters, like order 10 centimeters, 5, 7, something like that. That would give you the kind of optical performance on the right there, and it would be low mass. We also have this D-scope on the right, which is responsive to the fact that the far infrared channels would require active cooling because we can't passively cool to 4 Kelvin where they would be sensitive. So we would need a solution to that problem, which I'll talk about in a sec. But in the event that we didn't do that, we could still do the 0.5 to 12 micron, let's say, imaging spectrometer very easily, purely passively. And that would negate any technology concerns we have, because that.
Hey, Mike, we've just gotten to 12 o'clock.
Okay, I think I'm on my last slide. Next slide. Right, so the last slide here is what's next. Basically, the programmatic considerations we have are that most of the technology we would need to build this is already off the shelf and flight proven stuff. There's 3 technology development areas I've kind of bulleted down at the bottom there. We actually put a poster in the poster session, so I'll, in the interest of time, skip over that now. But if you're interested in what kind of technology development we would require, we can talk about that during the poster session. There's a fundamental question here that we haven't been able to kind of close out that I wanted to raise, which is, can we accommodate a spinning spacecraft, similar to Kirby's concern? With being clever and doing some technology development and making some very specific architectures, it's quite possible we could do a lot of this from a spinning spacecraft as well. I guess the question at this point is, and this isn't a question for this study, but going into the future, if we made that effort and did all that development, would it be possible to squeeze this on a spinning spacecraft? And I think Kirby has the same question. The box on the right there is really just about the strategic plan, which is that we've already talked to the astrodecadal. The white papers about this sort of thing were submitted to the planetary decadal, kind of talking about the dust science we can do. And our goal is to support an engineering, a real engineering study for what would we actually propose in a few years, doing technology development. Okay, with that, I will stop.
Thank you very much, Mike. There's a few questions in here. I think we can mostly answer them offline, but there were 3 suggestions actually from Tony Freeman about other possible science augmentations that could go along with this, including a gravitational wave detection, a possible quantum communication experiment, and so forth. But I really like the spirit of the questions that were asked, Mike. They're right in line with the way you've approached this from the beginning, which is, we're going there. What is it that we can do to make this, you know, the Vanguard mission, if you will, that it should be? We're going to be in this space, and we should do everything that we can to take advantage of the position that it has. All right, so everyone, we're going to take a break now until 12:30 Eastern time. I hope you get up, get some refreshment, stretch a bit, and we will see you again in a half an hour. Thank you very much to Mike and all of our speakers this morning. We'll see you again real soon.